Okay, so I've just started this now, so we'll give it a second.
Hopefully the security guy is not going to come to close the building.
Yeah. Well, hi everyone, thanks for joining. We're just going to give it another minute or two just to let everyone join, and then we'll kick off. Okay, so I'm going to kick off now. So hi everyone, and welcome to tonight's webinar, and thank you all for joining. My name is Katie and I'm on the communications team here at SIMS, and tonight we're joined by Iulian Roman, our Clonskeagh Clinic Lab Manager. So I'll just give you a really quick brief intro to SIMS before I hand you over to Iulian, and if you have any questions throughout the night, you can pop them into the Q&A box and we'll answer them at the end. So at SIMS IVF, we have 6 clinics in Ireland. We have 3 main clinics located in Clonskeagh, Swords and Cork, and we have 3 satellite clinics in Dundalk, Carlow and Limerick. SIMS is also part of the Virtus Health family, which is one of the world's leading fertility groups. So we get to share experience and knowledge from all around the world. And this ensures that our patients get access to the very best care and expertise. At SIMS, we have a range of treatments such as fertility testing, IVF and ICSI, and we have donor egg and donor sperm programs, and we also offer genetic testing options. We have a range of options and treatment pathways as well for solo motherhood and same-sex couples. And we recently have a new partnership with My Surrogacy Journey, offering some surrogacy supports as well for Irish intended parents. So with that, I'm going to hand you over to Iulian, and he'll take you through tonight's webinar about embryo development and embryo grading.
Thank you, Katie. Thank you for the introduction. Thank you, everybody, for attending this evening. So I'm going to start my presentation basically on embryo development and embryo selection tools and how we use them to ensure that we fasten the route to your pregnancy. So how do we know, how can we test the quality of the oocytes of the embryos? Both the oocytes and the sperm are very unique cells. They have a very unique nature, and because they're single cells, there's not much invasive testing that we can do on them. Basically, once you have done invasive testing, then you can't use them anymore. So there are a lot of other options here, just a brief presentation. We can test proteomics, we can test metabolomics, or even the genetics. Most of the stuff, most of us heard it only on, like Big Bang Theory. In fairness, the most reliable way to test the quality, to see the quality of the oocytes of the embryos is still looking them through microscopy. So whenever we look at stuff with our own eyes through the microscope, basically it transforms it into a beauty contest. So before we go and assess what beauty means in this embryology field, I'm just going to go very quick to the embryo development timeline. So on the day 0, on the day when we have the egg collection, we have the eggs collected. Initially, they're surrounded by a bunch of cumulus cells, the support cells for the maturation of the egg. Then we get rid of them before we do the insemination, and we can clearly see the egg. On day 1, we need to see the fertilization signs and possibly the first cleavage of the egg cell. And then, as day goes by, the number of cells multiply until they reach day 5 or day 6, when we have the blastocyst. When the embryos reach the blastocyst stage, which is the stage that we are doing now, the vast majority of our embryo transfers. So the first take when we look at the oocytes is at the egg collection. This is how oocytes look. We have the oocyte in the center, surrounded by some closely intimate cells. Those are called the coronal cells, and some larger layers of other cells, the cumulus cells. So all these cells are basically mediating they're mediators between the hormones in the bloodstream and the maturation of the oocyte. In the initial years of IVF, there were attempts to start grading the oocytes at this level. We can look at how expanded are the cells more closely to the oocytes and how expanded are the cells, the cumulus cells. Even though there was a lot of work on trying to grade and to predict the outcome at this stage, what we've learned afterwards is that at this level, the most reliable thing that we can predict is the maturation of the oocyte. So the aspect of the oocytes at the egg collection doesn't necessarily have, a good prognosis on the outcome of a cycle. So when we're talking about the maturation, we eliminate the cells around the egg, and we actually see the oocytes in 3 stages. So the first stage is the germinal vesicle. We recognize it by seeing this circle with a dot inside. So basically, that's the nucleus of the cell. All the oocytes have this shape since the birth of the female until just before the ovulation. Okay. An intermediary state is, we see here a clear oocyte without that visible nucleus, which is called the metaphase 1, which means that the egg started the maturation process. And the last stage is metaphase 2, which we consider a mature oocyte. And how we distinguish this is the presence of this small globe here, which is called the polar body. This is basically indicating that the oocyte has eliminated half of the DNA in preparation to accept the other half coming from the sperm cell. So this is basically an ideal oocyte. As you can see, it has multiple structures. So we have the oocyte itself. When we're looking at this, we need to see a clear cytoplasm with uniform granulation, nothing that pops out as abnormal. Then we have the polar body, which needs to be either round or oval and closely attached to the egg. And we have the outer shell, the outer shell of the eggshell, basically, which is called zona pellucida, which is a glycoprotein structure that protects the oocyte until it reaches the blastocyst stage and hatches out. And we also look, when we're grading the oocytes, at this space between the zona pellucida and the oocyte itself. So as I said, this is an ideal looking oocyte. The reality is that we see a lot of non-ideal morphologies. Here we see all kinds of abnormalities, either in the size or shape, both of the oocyte or the zona pellucida. This is, some of them are 99.9% related to genetic imbalances. Like we have here this giant oocyte. You can see the size of this is way larger compared to the other, or when we have this kind of oocytes with a very large polar body. These are definitely signs that we have quite imbalance in the number of the chromosomes inside the oocytes. All the other abnormalities, they appear in the vast majority of the cycles for some of the eggs, even though they're related to decreased outcome of the cycle. That doesn't necessarily mean that they don't have potential to form a blastocyst, generate a pregnancy, and then result in a live birth. So very few things that we actually select at this point. All the mature eggs are going to be used for insemination. And after insemination, the second day, we look at the fertilization. So what we need to see at the fertilization is inside the oocyte, we see these small circles with those dots inside. Basically, they're the nuclei, one from the egg, one from the sperm, coming together to form the new genome of the future baby. Somewhere up to 10% of the fertilized oocytes have abnormal fertilization. So either we see only one pronuclei or 3 or more pronuclei. We are learning now that the one with only one pronuclei, they might have reasonable chances to actually be normal. But the ones that have 3 or more pronuclei, the vast majority of them, they have genetic imbalances. So apart from the cases where we test the embryos for genetic screening, these kind of oocytes are not going to be kept. They're not going to be kept in culture, and they have also lower chances to actually develop to the blastocyst stage. Just to go to make a bit of history, in countries where embryo manipulation was banned until quite recently, in Central Europe, countries like Germany, Austria, Switzerland, and to some extent Italy, the selection, because of the legislation, the selection had to be done at this point. So during the 2000s, in the 2000s, a lot of research was done, and a lot of correlation of the shapes of these pronuclei and how the small dots are distributed inside to create grading systems. There were plenty of papers who claimed that selection based on this grading was actually very good, until research from other countries where this legislation wasn't enforcing selection at this point came out, and we then realized that this kind of grading doesn't improve the outcome of a full cycle. So after the fertilization, what we need to see is cell cleavage. So from one cell, it divides into 2, and then from 2 to 4. On day 2, we need to see between 2 and 4 cells. And on day 3, we need to see anywhere between 6 and 10 cells. So the vast majority of embryo transfer until 10, 20 years ago were done at these stages. It was in many cases they were transferring more than one embryo just to increase the chances of a pregnancy. And how we select the embryos back then was looking at 3 main things. So one of them was the number of the cells. The second was the evenness of the cells, so how even all the cells are. And the first parameter that would look was the fragmentation that happens. So you can see here on images D, E, and F that we have increasing amounts of cell fragmentation. Now this fragmentation was a lot of research was done to try to explain what are the reasons behind this fragmentation, and up to this point we can't point to one single cause for generating this fragmentation, but it's present in the vast majority of the embryos especially after the first cleavage. But the level of fragmentation is definitely something that we look out even now before we select the embryos. The higher it is, and the lower the potential of the embryo to develop into blastocyst. So this was back then. Now we are doing mostly 100% of the transfers at the blastocyst stage. Actually, Sims IVF was the first clinic to introduce the blastocyst culture in practice. This basically means that we keep the embryos beyond day 3 until day 5 or day 6. Some of the embryos just need another half day or even a full day to actually reach the blastocyst stage. So there were significant benefits after introducing this extended culture period. Basically, we had more information on how embryos develop after that stage, and we had the ability to assess whether the embryo were developing normally after the day 3 or not. We have a better synchronization with the womb, because on day 2 or day 3, normally the embryos don't reach the womb cavity and they're still traveling the fallopian tube. And also, very important, we have improved the pregnancy rates after a single embryo transfer. One of the main concerns in the IVF field was, after the initial 20 years, let's say, was to decrease the number of multiple pregnancies. Obviously, this is something that we don't necessarily want to achieve, because of the complications that might arise afterwards. So when the embryos reach the blastocyst stage, they look very different from what they looked on day 3. They're not just some cells that all of them look the same. We have 2 different structures. We have here a compact mass of cells, which is called the inner cell mass. That is the part of the embryo that would actually form the baby, and all the surrounding cells, the surrounding layer in the globe shape, are trophectoderm cells. These trophectoderm cells are responsible to generate the implantation, and later on they will form the placenta, the embryonic part of the placenta. So what we're looking at this stage is this inner cell mass to be a nicely compacted mass with a good number of cells, and the trophectoderm cells to be evenly distributed, more or less the same size, and to see a good number of cells. So just by comparison, here we have an embryo that has the trophectoderm, looks absolutely beautiful, but you can see the inner cell mass. It's fragmented. It's not a compact mass of cells. So that's a grade C in this case. Or here we have an embryo that has a compacting inner cell mass, which is in between A and C, so it's a grade B. But you can see the trophectoderm cells. Some of them are small, some of them are medium, some of them are large, with even gaps between them. So this would be a grade C in terms of the trophectoderm. So after introducing all the culture to the blastocyst stage, the next improvement, let's say technological improvement, was the introduction of the time-lapse imaging of the embryos. So to understand what this time-lapse means, basically we have an incubator that has a camera integrated inside, takes the picture of the embryo development at every 10 minutes, and at the end of the cycle, it generates a video with all the development of the embryo. So just to exemplify here, we have an embryo that after fertilization check was cultured until day 5. So I'm going to play the video now. So we see the fading of the pronuclei and the first cleavage. As you can see here, we have the second round of cleavage, 4 cells. So this is around day 2. And then we see 8-cell stage on day 3. And after the 4th round of cleavage, we see this process of compaction. So this is what an embryo looks like normally on day 4. All the cells are gathering around, and in terms of grading, there's not much we can actually assess at this point. It's just the presence of this compaction that it's indicative that the embryo is going further. And then afterwards, we can see, after a couple of more cleavages, we can see here the forming of the cavity and the separation of the 2 types of cells, which eventually form very nicely. And we can see a clear inner cell mass, a beautiful trophectoderm. So this is a top quality embryo. So what we've learned after this was quite the revolution in our field. Basically, just to make an analogy, with the famous stars, actors, and stuff like that. So during the 80s, 90s, and in the early 2000s, you would have an actor giving an interview once a year in a famous magazine, and time lapse is basically similar to our today's social media, where we can't go anywhere without knowing every second of the new star's life. So this time-lapse imaging offers also other advantages, because We don't need to take the embryos out to put them under a microscope to assess them at certain times. So it's an undisturbed culture. After the fertilization check, the embryos are not going to be disturbed at all until they reach the blastocyst stage. We can assess not only how embryos look, but how they got to certain stages with the advent of morphokinetics. We have the option to actually look at the embryo development, not just while it happens. We can, retrospectively look at the embryo, how much time, and we actually spend more time on analyzing the embryos and how they reach certain developmental stages. And we also have algorithms developed on this developmental, which I'm going to show you just a bit later. There is a lot of stuff that time-lapse allow us to see that we didn't actually saw before, only by analyzing embryos, just snapshots of their development. So just to make an example here, we have one cell that instead of developing into 2 cells, it's cleaving into 3 cells, so that would be called direct cleavage. It's most of the times it's abnormal. It's an abnormal event that triggers a sign, and we label these embryos in yellow, so not green, not red. They still have potential to develop further, but that's definitely an exclamation mark on this embryo. So it probably in selection would be a bit downgraded. Now we have an embryo that was trying to cleave. You can see the top cell here, but it didn't actually cleave. So that's called a failed cleavage. But even so, the embryo manages to develop into a decent quality blastocyst, as we see here. And in the cell mass, that looks good. The trophectoderm is not ideal. And here we have another example of abnormal cleavages. So we can see this embryo developing from 2 to 5 cells, and then 2 of the cells recombine together. You can see here more nuclei in this cell. So these are all things that we couldn't see them before, but now we see them, and this is also part of the selection criteria when we're talking about embryos. Priorities to prioritize the embryos for the embryo transfer. But probably the most important stuff that this time-lapse technology came with is the development of algorithmic scores. So basically, we are recording all the stages when they reached 2 cells, when they reach 3 cells, 4 cells, and so on until they reach the blastocyst stage. And this is actually called a KID score. So KID comes from known implantation data. So all these patterns of the embryos on reaching the time points were compared to tens of thousands other embryos which have a known outcome after their embryo transfer. So the grading is done. You can see here 8.5. It goes from 1 to 9.9. Obviously, the higher the score, the better the chances of that embryo to generate a pregnancy. So there's definitely improvement this was definitely improving the selection criteria, especially in the first years after the introduction of the time-lapse technology. Not just us, but the vast majority in the IVF clinics around the world, they have seen the results of a better selection of the embryos. And improving the pregnancy rates after the first transfer. So after the time lapse, the next step on technological development was the artificial intelligence. So we were lucky enough to be one of the first clinics we were involved in the development of the most commonly used AI embryo selection tool. AI has some advantages. The human brain can work around 20,000 different data points when making decisions, but the AI does not have such limitations, and it allows to look at things that we might not see, or even if we see them, it's quite difficult for us to put a weight on how those events might impact the outcome of the embryo, to quantify them, or just things that we don't necessarily think they're important. So just a proof of concept. Sorry. So just a proof of concept, we asked the developer who generated this AI tool to review YouTube videos of different sports and get to determine which sport is what. And obviously that was too easy. Next, we asked the developer to take videos of horsing events and have the AI determine the difference between steeplechase, show jumping, or dressage. And this was easy for a human, but not so much for AI. Well, not so much, but in the end, the AI managed to distinguish between them. And we were quite surprised to see that the most important thing for AI to actually discriminate between this type of contest was the angle of the horse hoof, which probably for the vast majority of the people, if they're not highly specialized in this field, they wouldn't think that this is the criteria that would make the difference, the most of the difference. So this was quite exciting to see, because, as I said, AI can look at stuff that we don't necessarily look at. So apart from the imaging that are fed to the AI, there are overlayers of stuff that we can't necessarily see. So here, for example, is a heat map. Other systems use granulation, pixelation of the images to determine some of the difference. So we can see here in this heat map, in the center, the red spots are the red is good. Let's make it easy, and the blue is not good. So you can see here that according to this heat map, it's something that the AI didn't like about the development of the inner cell mass and the cavity of the embryo. And development of these AIs actually make life easier for us to distinguish between to make a faster grading of the embryo. So basically, the AI looks at this and starts grading the embryos very similar to the morphokinetic algorithm, and puts a score again from 1 to 9.9 in order for us to rank the embryos and to select the best one for the next transfer. There is another way that embryo selection works, and the other way is basically testing the genetics of the embryos, because even if AI and time-lapse improve the selection process, there are still limitations, and there's still quite a gap in our knowledge about the embryos. So in order for us to know if the embryos are genetically normal, we need to take a small sample of the trophectoderm, put it in the tube, and send it for genetic analysis. I'm just gonna show you a quick version of an embryo biopsy. So basically, we are making a hole in the zona in the eggshell, and with this pipette, we're gonna aspirate some of the trophecta themselves. So all this zona cutting is done with the laser, very precise laser. And when you get in, we aspirate some of the cells, we actually realized while we're learning this that the embryo at this stage is quite tough. It's not even though they might seem very fragile. This technique is a bit invasive and requires a bit of strength to do it. So after we aspirated those cells, we just flick that part to collect it. Okay. At this point, the embryo is going to be frozen, and that small sample of cells is going to be sent for genetic testing. So what we look at genetic testing is to see if the embryo has the normal number of chromosomes. So we see here an embryo from a female and a male embryo. We have the middle line, which represents basically two chromosomes from each pair, from 1 to 22, and one of each X and Y chromosomes for the male, and two X chromosomes for the female. So this is a normal test, and abnormal, we would see something result something like this. So all the chromosomes apart from number 16 in the top. So we can see the pair number 16 has only one chromosome instead of two, and in the bottom image we see that chromosome 13 has actually three chromosomes instead of two, so either a monosomy or a trisomy. These findings are quite they have a high frequency. It's very much correlated with the age of the patient. So the older the female patient, the more of these aneuploidies that are found. And I'm going to show you now the set of 9 embryos that again develop from fertilization until the blastocyst stage. So out of these 9 embryos, we're going to have at the end 6 embryos that are going to be biopsied. Okay, so number 2 here, number 7 and 9, they're not suitable for biopsy. But when we did the genetic testing, we actually saw that only 4 of the 6 were normal, and arguably the best one, which was number 5 here, actually came back with aneuploidy. Now these aneuploidies are quite tricky because, as you can see, the embryos can develop quite well. If we transfer such embryos, they might even generate a pregnancy. So we might actually have a positive pregnancy test. But what happens afterwards, the vast majority of these embryos result in early miscarriage, somewhere between weeks 6 and 10. So testing the embryos genetically basically, first of all, improves the chance of viable pregnancy. It's when we're transferring normal embryos, we decrease significantly the chances of miscarriage. And in cases, and another advantage is that we don't transfer these aneuploid embryos, so we don't go through the financial burden of another cycle for an embryo that's not going to be successful. So there's a lot of talk about how to combine, how to get the best decision on using all these types of testing. So basically what we do is we use all of them. We use both time-lapse, the morphokinetics, the AI, and the genetic testing. We are actually running now, almost finishing a research trial to dig in more into the limitations of the time-lapse and the correlations between time-lapse, morphokinetics, AI, and the genetic testing. Because one of the goals in this field is to start having reliable, non-invasive testing. As you could see earlier, the biopsy of the trophectoderm is a procedure that's not accessible for everybody. Here in our lab, only the senior staff are doing this procedure. And even though the data doesn't necessarily show that the biopsy itself is detrimental to the outcome, it's still an invasive procedure. So we're looking forward to, get other stuff to develop new things that are going to be reliable enough and more cost effective in order to select the best embryos without necessarily putting them under the pressure of genetic testing. So our hope, especially in the lab, is very much as for our patients, we are evaluated based on the success rates. So hopefully, when somebody has a cycle here, it's going to be the successful one. Thank you very much. Thank you for listening. And now, if you have questions, I'll be very happy to answer you.
Thanks, Iulian, for that. It was really, really great to go through that, and the videos and the pictures were really clear as well. So thank you. And if anyone has any questions, you can pop them into the Q&A box as well, and we can do our best to answer them. If you have as well any questions that you don't want to ask on the webinar, you can email communications@sims.ie. I can put it into the chat as well. And one of the members of the staff or Iulian can get back to you as well. I can pass the question on to him. So if anyone has anything that they don't want to openly discuss, that's no problem at all. So there's a few questions in at the moment, Iulian. So one of the questions is, do you recommend PGTA before all transfers? If embryos are frozen, is genetic testing possible prior to a transfer?
No, we don't recommend PGT for all cases. Obviously, PGT comes with a cost. Probably the main groups that would benefit from PGT are the age group between 35 and 39. So that's the first group, and the reason for that is that those are the patients where we get most of the cases more than a couple of embryos. So it's actually a reliable selection tool because we have a good number of embryos where to select from. Before 35, below 35, it wouldn't necessarily be an indication for PGT because it's a way higher incidence of normal embryos. Now, after 39, 40 years of age, the discussion is how useful is the PGT. I can see now that in US, for example, it's very largely exposed that the PGT should be done for everybody above 40 years of age. It's obviously the incidence of aneuploidy of abnormal embryos is higher after 40. It kind of drops slowly between 35 and 39, but after 40 it drops quite a lot. Basically, it's down to somewhere between 1 in 5 or 1 in 6 embryos are actually normal. But the thing is that after this age, it's actually harder to get those 5 or 6 embryos. So for most of the cases, would require more than one cycle to actually get that number of the embryos to actually have a chance for having a normal embryo. This is one of the reasons why we have developed the banking cycles. So basically, I think we have up to 4 or 6 embryos. So if we don't get to that number in one cycle, in the next cycle, we can do another cycle that just to get the number of the embryos growing for testing. It's definitely, it has this method, like all the time lapse and AI and embryo testing, none of these, bear in mind that none of these are improving the quality of the embryos. So this is just to select them. Biopsy itself doesn't improve the quality of the embryo, but selecting the embryos genetically, as I said, avoids a lot of embryos that we wouldn't transfer normally, that we might transfer normally if they weren't tested, because they're good looking embryos, but it definitely decreases the rate of early miscarriage, which is quite unpleasant for patients to go through. So we have to bear this in mind. Now, for the second part, if embryos are already frozen, yes, they can be tested. For that to happen, we need to thaw the embryos, we need to do the biopsy, and then we have to refreeze them. Now, the question would come, okay, how does that impact the quality of the embryo? Because obviously the same embryo was thawed and frozen twice before it actually goes to transfer. Now, I would probably say, straight out of my mind, that probably the impact is somewhere around 10%. But when we actually look at the numbers that we did for this kind of cases, the pregnancy rate didn't actually decrease at all. It was more or less the same with what we normally do. Now, on the other hand, we don't have that much data, and not even in the literature. They're not, comprehensive research to actually back up this assumption that it doesn't have any effect. The risks are, like the embryo is going to be manipulated twice through some procedures. All of these procedures are not naturally occurring in natural life, neither thawing, freezing, neither the biopsy. But as I said, from what we've done so far, we didn't see any detrimental impact on further outcome.
Thanks, Iulian. And there's another question that's come in as well about the PGTA testing and the biopsy. So does that harm the embryos, or is there any risk of damage to them if you do PGTA?
Well, it's obviously, as I said, it's an unnatural procedure, so it's an invasive procedure. Now, normally we would assume that this would have an impact. Before going to trophectoderm biopsies, actually the biopsies 10-15 years ago were done at day 3 stage, so they were taking one cell out of the embryo. That seemed to be more detrimental to the embryos, to potential to implant, first of all. But when we're talking about trophectoderm biopsy, tested embryos, tested euploid embryos, they have actually a higher implantation rate than untested embryos. Now, this is obviously because the untested embryos, the non-biopsied embryos, we don't know actually if they were genetically normal or not. But so far, it doesn't seem like there is a major detrimental impact while doing the biopsies on the embryo and use them afterwards in a frozen embryo transfer. The survival rate of the embryos biopsied and frozen, it's the same as for regular embryos, somewhere around above 95, between 95 and 98% survival rate. But once the transfer is done, we can't actually assess what's happening afterwards. The biopsy procedures are well established now. We are doing here biopsy since 2018, I think. We've done thousands of cases so far. So in very rare instances, we had an embryo not surviving after a biopsy.
Thanks, Iulian, for explaining that. And how long does the PGTA testing take?
The testing itself.
Yeah, so when could someone expect maybe results back?
Yeah, so after, we don't do the genetic testing in our building. We send it to a genetic testing provider. Usually we have the deliveries on Wednesday, so everything that was done between up until midweek is going to be sent, and then we have a waiting time of 6 weeks. Now, this is the vast majority of the cases. The results come up a bit earlier. But this 6 weeks time is basically, enough time to schedule a return consultation to discuss the results of the biopsy cycle and put in place a treatment plan for the frozen embryo transfer. But yeah, from the egg collection cycle until the transfer, it should be done if no other contraindication, should be between around 2 months.
Great, thanks, Iulian. Just give it another minute or two and just see if there's any other questions coming in. I've also just put the communications email into the chat as well. So again, if anyone has any questions that they think of later or they want to talk about offline, please feel free to email them into the communications email, and I'll pass them along to Iulian and he can get back to you as well on them. So does anyone else have any more questions? So there's just a question after popping in there, Iulian. Should donor embryos be tested for PGTA?
Well, it depends what donor. If it's donor sperm or donor egg, obviously for donor egg, there shouldn't be the indication there, because all of the egg donors that the egg donation program that we're running, the donors are way below 35, so they're young donors. I think that's selection criteria to any egg donation bank. When we're talking about sperm, the most important factor is the female of the age of the recipient. Only about less than 5% of the aneuploidies are actually are coming from the sperm cells, and again, the sperm donors are very young, so that's quite unlikely that the aneuploidies come from the sperm. 95% of the aneuploidies happen because they happen in the egg during the maturation of the egg. So, as I said, for egg donors, I wouldn't necessarily consider it an indication. But for sperm donors, again, the most important is the criteria is the age of the female.
Great, thanks for that, Iulian. So I don't think there's any more questions in, so I think we can leave it at that then, Iulian. And again, if there's any questions come in, I'll pass them on to you as well. But thank you very much for going through all that. It was really, really informative.
All right. Thank you very much.
Thank you.
Have a great evening.
Thank you. Bye.